We are the Rocket Watch group, and this is our project on the GEO Satellite Threat Assessment System. So this semester, we worked with the Lawrence Livermore National Lab and the SDA TAP Lab, standing for Space Domain Awareness, Tools, Applications, and Processing. This is a lab in Colorado Springs that was designed to stimulate innovation and collaboration between industry, the government, and academia to solve the operational needs of the U.S. Space Force. Moving on to our problem statement, the project we worked on was the development of a tool to detect if a rocket is launched directly from Earth to geosynchronous orbit, or GEO. Will this be a threat to satellites in GEO?
We rely on satellites in our daily lives for everything from navigation to communication to weather forecasting, meaning that it could cause widespread disruption if one were to be removed from orbit. Not to mention that these satellites can cost up to $400 million and collisions would generate debris in space. To identify when satellites could be at risk, our team developed a Python tool to simulate and optimize the trajectory of a rocket given rocket-specific inputs. The tool visualizes the trajectory of the rocket and finds the closest possible distance to a satellite within constraints. Finally, the tool outputs if that distance puts the satellite at risk, which is defined by the TAP Lab as 200 kilometers.
Out of our model's hundreds of lines of code, some of the most critical constraints are related to this ordinary differential equation that the team developed, shown here as equation 2. Its basis is Newton's second law, and at a high level we see that the weight force of the rocket is being subtracted from the thrust force, with this being equal to the net mass times acceleration of the rocket. Equation 1 shows one instance of another constraint that is related to this ODE, in that the change of mass is defined in relation to the thrust. When gathering satellite data to assess if one satellite is in danger of close approach with the rocket, we read in the satellite's current position and other metrics using an API at the start of the detected rocket's launch. The data is collected in the form of two-line elements.
To analyze our results, we plotted 3 different graphs to see the most crucial variables, so velocity, thrust, and position of a rocket. You can see it in its 3 different components on the plots, and the red line depicts the overall velocity and thrust of the rocket. And for the trajectory of the rocket within Earth, we have 3 different plots showing different locations of launch as well as different satellites. So there might be a different path to hit the satellite or different velocities used. But in this case, all 3 do represent a collision approach.